This is a sphere, this is a sphere, and this is a sphere. And these are all circles. By the end of this video, you will understand why. The theory of Banach spaces has its origins in the early work of a Polish mathematician named Stefan Banach. In his Ph.D. thesis, Banach established the first complete definition of these spaces, and consequently gave birth to an entirely new area of math known as functional analysis. To say that Banach's career path was unconventional is quite the understatement. After graduating from high school, he concluded that there was nothing new to discover in mathematics, so he decided to study engineering at university instead. Years after completing his degree, a chance encounter would change his life forever. One day, Banach and a friend were sitting on a park bench discussing a branch of math they recently learned called measure theory. Just then, Hugo Steinhaus, a prominent mathematician, walked by and overheard the words Lebesgue measure. Overcome by curiosity, Steinhaus immediately introduced himself. They all quickly became friends, and just days later, Banach would solve a math problem that had been plaguing Steinhaus for some time. As Steinhaus wrote in his memoirs, "From then on, we would meet on a regular basis, and we decided to establish a mathematical society." Now in his mid-20s and realizing that there really was much more to be discovered, Banach thrived under Steinhaus's mentorship and lived the life of a research mathematician, without any degree in math whatsoever. He would ultimately receive his PhD years later when another professor stapled his many publications together and tricked him into doing a thesis defense. An influential part of this unconventional thesis was the definition of a new mathematical space that leads to weirdly interesting geometries. Geometries where spheres become cubes, circles become squares, and pi equals 4. This weirdness is a result of the various ways that length can be defined in Banach spaces. The technical description is that there are many ways to define a norm on a Banach space. This abstract conception of length turns out to be one of two key features that define Banach spaces in general. So from the mathematician whose career trajectory went completely against established norms, we now turn our attention to his precise notion of a mathematical norm. To get some intuition, let's begin by considering 2 points on the xy plane. We can use the Pythagorean theorem to calculate the distance between them. And in general, we can use this form of it to calculate the distance between any 2 arbitrary points in the plane. But we can also change this setup to get a slightly different notion of distance. Suppose the plane turned into a grid, and you weren't allowed to cut across. So the only way you can move from one point to another is by traveling along the lines of the grid. The distance between 2 points now becomes much simpler. Instead of a squared plus b squared equals c squared, we have a plus b equals c. So in this specific example, the distance between these points is equal to 4. And for any 2 arbitrary points, the general formula for distance will be as follows. Because of its resemblance to the famous Manhattan grid structure in New York, this type of geometry goes by the name of the Manhattan geometry, or the taxicab geometry, while the usual notion of distance we began with is referred to as Euclidean geometry. The taxicab geometry seems innocent enough, but it has some non-intuitive consequences. Recall that a circle is defined as the collection of all points that are the same distance away from the center. So a circle of radius 2 in Euclidean geometry looks exactly as we'd expect. But in taxicab geometry, if we consider all points that are a distance 2 away from the center, we get a much different looking shape. This diamond shape really is a circle with a radius of 2 in this alternative geometry. And even more interestingly, we can calculate a new value of pi. Pi is defined as the circumference of the circle divided by its diameter. The length of each side here is 4, which means the circumference must be 16, and the diameter is 4. So in taxicab geometry, pi equals 4. There is still a third way we can define distance to produce an alternative geometry. Suppose you still had the grid structure of the taxicab geometry, but now the total distance is defined by just taking the maximum distance traversed in either the x direction or the y direction. So in this case, the distance between these points is 4. And the geometry that results from this notion of distance is called the Chebyshev geometry, named after the Russian mathematician Pafnuty Chebyshev. Here, a circle of radius 2 looks like what we typically think of as a square, and pi is equal to 4 once again. So how does all this connect to Banach spaces and norms? Well, all three of these spaces are actually Banach spaces, with each having their own unique norm defined on them. Although I've been talking about the general concept of distance between points, a norm is just a special case of distance. Whereas distance is something defined between any 2 points, a norm instead is the length of a vector, which you can view as the distance between the tip of the arrow and its tail. But this applies not just to arrow and space vectors, but to any abstract mathematical vector. So just as we had 3 different rules of defining distance in these spaces, we also have 3 rules for how to define the length of a vector. All of them are mathematically consistent and satisfy the following criteria, which is the precise general definition of a norm. Any space that has some rule specifying what norm is defined on it is called a normed space. So in the hierarchy of mathematical spaces, we can begin with a space that is just a collection of abstract vectors. This naturally is called a vector space. At this stage, there's no way to measure lengths of vectors or angles between them. In order to do so, we define an inner product, which is essentially just a generalized dot product that satisfies these criteria. The vector space now becomes an inner product space. If we are only interested in measuring lengths, however, but not angles, we can define a norm on this space instead. Frequently, the norm of a vector can be defined by first finding the inner product of a vector with itself, and then taking the square root. In this case, the norm will logically depend on the inner product. The technical term that's used is that the norm is induced by the inner product. Not all norms are defined in this way though. Some have absolutely no connection to inner products. In fact, there is a convenient theorem that says that the only situation where a norm depends on an inner product is when something called the parallelogram law holds. Consequently, all inner product spaces are normed spaces, but not all normed spaces are inner product spaces. Now, lengths of vectors are just specific ways to measure distances. The more general mathematical notion for distance is called a metric, which is a function satisfying these criteria. And just as an inner product induces a norm induces a metric. But not every metric comes from a norm. So defining a metric on a space leads to a much more general class of spaces called metric spaces. This results in a neat hierarchy of spaces, where each smaller space is a special case of the larger space. So every inner product space is a normed space, and every normed space is a metric space. A Banach space therefore lives in the middle here. It's a normed space with one additional criteria, namely that it's complete. What it means for a space to be complete is that the limit of any converging sequence exists in the space. More precisely, for any Cauchy sequence, if the Cauchy sequence converges to something beyond the space, then the space is incomplete. But if you extend your space so that every Cauchy sequence now converges inside of it, then the space is complete. There are many examples of this, and I explained what all this means in detail in one of my previous videos, which I've linked below. So if you'd like a more comprehensive explanation, then be sure to go check that out. At this stage, I'd like to clarify the precise difference between a Banach space and another important mathematical space, a Hilbert space. While a Banach space is a complete normed space, a Hilbert space is a complete inner product space. This means that a Hilbert space is a Banach space where the parallelogram identity holds. And while any Hilbert space is necessarily a Banach space, there are plenty of Banach spaces that are not Hilbert spaces. To highlight this distinction, we will consider a family of Banach spaces that are directly related to the circles and spheres we saw at the beginning of the video. The LP spaces. The LP spaces are spaces that consist of all sequences where this sum is finite. One space exists for each p-value that's chosen. So for p equals 1, L1 is the space of all sequences where this sum is finite. For p equals 2, L2 consists of all sequences where this sum is finite, and so on. We can define the following norm on all of these spaces to turn them into normed spaces. Every single one of these spaces is also complete, which means they are Banach spaces. Not only can we choose various p-values to form different Banach spaces, but for each p-value, we can choose a different value of n here, which will correspond to the dimension of the vector. In 2D, for p equals 1, we get the L1 norm. So the length of an arrow would be calculated as follows. And from the L1 norm, there is a natural metric that can be defined, leading to the taxicab geometry. For p equals 2, we get the L2 norm, which leads to Euclidean geometry. And then there's the L infinity norm, which leads to the Chebyshev geometry. Before seeing what happens at all the other p-values, let's see how this looks in 3D. Now, why did we only consider p equals 1 to infinity? What about the values for p equals 0 to 1? Well, remember how metric spaces were more general than normed spaces? From p equals 0 to 1, these sequences form metric spaces. But the metric defined here does not come from a norm. There's no way to define a function in these spaces that is consistent with the definition of a norm. Once we hit p equals 1, all of that changes. From here on, every single one of these metrics comes from a norm. And there's only one norm that is induced by an inner product at p equals 2. So L2 is the only Hilbert space amongst these infinite number of Banach spaces. A big thank you goes out to this video's sponsor, Brilliant.org. Getting good at math requires utilizing good resources, doing tons of practice problems, and getting reliable feedback. Brilliant covers all three of these. Its courses are packed with tons of lessons on topics ranging from basic algebra all the way up to learning how to think and code, and even understanding how AI works. One of my favorite aspects of Brilliant's approach is that each lesson always builds up your intuition for the math and instantly provides great feedback with interactive visuals along the way. If you pick any one of the thousands of available lessons, you'll also find plenty of practice problems to test your knowledge and sharpen your critical thinking. So if you're interested in a good resource where you can learn all sorts of interesting math and science, or even learn how to code, I recommend checking it out. You can try everything Brilliant has to offer for free for a full 30 days. Just visit brilliant.org/abidebyreason or click on the link in the description. You will also get 20% off an annual premium subscription.